Hello and welcome back to the weekly live sessions on mechanics and control of robotic manipulators. I am Isaac John. I'll be handling the weekly tutorial sessions on NOC105. So we have now headed on to week 5. So essentially, this is an 8-week course. We have done or we have progressed through halfway. We have progressed halfway through the course. And thus far, the topics we have covered was all about kinematics. So from this week onwards, we would be moving on to the later part of mechanics, which concerns with dynamics of a robotic system. So I hope we have gone through the lectures. The participants have gone through the lectures. And in dynamics, what we would do is we would consider the effect that causes the robot's state to change. So like, for example, until kinematics, we were just dealing with the geometrical relationships between the robot's joint space and the robot's task space. And in the previous week, on week 4, we have also used the geometrical models for analyzing the robot singularities and also to analyze the workspace of the robotic mechanism. But then, however, we completely ignored the forces or the external effects that causes the motion of the robot themselves. But in dynamics, we would also accommodate the external forces, moments, and how the interaction of a robotic manipulator on with the external forces, external disturbances, and the input forces and torques provided by the actuators, how these force and moment interactions would cause the robot to move or to change its state. So one such example is that, like, we'll consider the case of a 2-hour robot, something like this, with 2 legs or 2 limbs connected by 2 joints. We have already seen the kinematic modeling of such robotic systems, right? How to map the joint variables, maybe theta1 and theta2, to the task space variables x and y. We have seen the 2 problems of forward and inverse kinematics. But in dynamics, what we would do is we would also be considering the external forces. Maybe if we have an end effector over here, and due to the robot's interaction with the environment, the end effector would be subjected to some forces, maybe Fx, Fy, and Mz. And maybe due to some external interactions with other rigid bodies, maybe there will be some contact forces acting on the robot, Fc1, Fc2, and of course, the gravity, the effect due to gravity, M1g, M2g. And then, due to the motion of the robotic manipulator itself, it will have some effects due to the inertia of the robot itself or inertia of the links themselves. So that will also cause some effect on the robot's motion. So one example is that, like, if you consider a 2-hour robot having some finite mass, and if you consider the direction of the gravity to be along the negative x-axis, vertically down, this is the direction of the gravity. What will happen if you simply drop, a 2-hour robot like this? How will it move? What will be the trajectory of the entire robotic manipulator if you simply drop the robot under gravity? So to predict, the change of state, or the successive trajectories or successive points of the robot, from an initial configuration to to maybe an end position or at the end of the time, you need to have a model that basically correlates the effects or the external forces, moments, the joint forces and torques into the motion of the robotic system. So that is why we would require a dynamic model for a robotic mechanism. So for the syllabus of week 5, we have essentially seen how to derive the equations of motion in a state space form, right? The governing equation of motion that connects the trajectory of the robot with the forces, the external forces as well as the motor, the actuated forces. We would obtain those relationships from an equation of motion. And then how do we derive these equations of motion? We have seen two methodologies or two formulations that would give you the same equations of motion. One would be the Newton-Euler scheme, and the other would be the Euler-Lagrange scheme. So whatever method that you would use, you will end up with the same equation of motion or the same dynamic models. But then, depending, there are some conveniences, on why you would have to choose a Newton-Euler method or an Euler-Lagrange method. Then in the lectures, in the weekly lectures, we have also seen some dynamic simulations of serial manipulators, performed in MATLAB. And at the tail end of this lecture series, we have covered, introduction to trajectory generation, how to define a trajectory if you want a robot to move from a start position to an end position. But then we'll leave the discussions on trajectory generation for the upcoming week, for week 6 live sessions. So moving on, let's have a recap on what robot dynamics is essentially about. Dynamics is a study of systems that undergo changes of state as time evolves. So if your robot is at a particular configuration at the beginning of the time, because of the interactions of external effects, what will be the final state of the robot, or what will be the state of the robot as the time evolves? So dynamics essentially is the study of system that undergoes a change of state. In mechanical systems such as robot manipulators, the change of state involves motion. So the external effects would cause the robotic manipulator to change from one configuration to another configuration through a series of intermediate positions. So in robotic manipulators, we basically we associate the change of state as the change of the motion of the manipulator itself. The motion can be considered as evolution of position and orientation and their time derivatives. So the motion can be characterized by the positions, the derivative of the position, which is velocities, and its derivative, which is the accelerations. And apart from positions, we would also consider the orientations, the angular displacements, their higher order derivatives, which are angular velocities and angular accelerations. So evolution of all the positions and velocities, be it linear or angular, we would all consider that in robot dynamics. In robotics, the dynamic equations of motion for a manipulator is utilized to set up the fundamental equations of control. So to design a motion controller, this is something that we would see in the subsequent weeks. To design a subsequent motion controller for a robotic system, we would need a very good approximation of a mathematical approximation of a robot, which would be provided by the dynamic model itself. So, we would consider the dynamic model of a robot as a very close approximation of the physical system itself. And we can test our controllers, or whatever be the case, our motion controllers or force controllers. We can test or we can design the motion controller around the dynamic model of the robot, so that some sort of a desired characteristic can be achieved, or some design or control specifications can be realized. But we'll save that for week 7 contents. And then what we essentially require from the dynamic model is essentially the governing equations of motion, right? So for any mechanical system, maybe if you consider the classic case of a spring, mass, and a damper, if you consider this to be a mass, connected to a rigid body using a spring and probably a damper, and if you apply an external force, the force balance would give you the governing equation of motion, something like the external force is nothing but mx double dot plus, kx, which is the spring constant, plus vx dot. This would be the governing equations of motion for a classic case of a spring mass damper. In case of a robotic system, which comprises of multiple rigid bodies, not just a single rigid body, surprisingly, the equation of motion looks very similar to, a single rigid body case. But in this case, our coefficients of these velocities, accelerations, and forces, they would be vectors and matrices, instead of a single scalar quantity. But then that is how, the governing equations of motion would look like. It's essentially a second order differential equation. So the dynamic equation, or the mathematical representation of a dynamical system, can be represented using this function where, this is essentially a mapping between the trajectory coordinates or the trajectory variables, where q would be the position coordinates and q dot is the velocity and q double dot is the acceleration, and tau would be the generalized vector of forces and torques, maybe a vector of forces and torques. The unit depends on what kind of joints or what kind of coordinates that you have in this vector, q dot or q double dot. For example, if your robot consists of only, revolute joints, and if you consider your generalized coordinates to be the joint variables of the revolute joints, all of the elements inside this tau vector will be torques. And if your generalized coordinates comprises of, linear coordinates like prismatic joints, then the corresponding terms inside the force vector would also consider forces rather than torques, right? So this is the general form, right? So something that the dynamics is something that maps the generalized forces and moments to the positions, velocities, and acceleration of the generalized coordinates. And we can also reduce that to a very familiar form, which is the torque can be obtained as a mass matrix, which is a representation of all the masses and inertias of a rigid body system, multiplied by a vector of accelerations, plus a vector that would contribute, to the joint, to the torques in the generalized coordinates. So this vector, it basically, we call this as a vector of Coriolis and centrifugal effects. Because due to the, compound motions of the rigid body links, it will basically have a component of Coriolis forces, and it will also have a component of centrifugal effects. So we combine them, we combine all of these other effects into a vector, but all the terms that have a coefficient q double dot, we would separate it as in this form, like a mass matrix multiplied by.
Sorry, we can't hear you. Thank you, sir.
Oh, okay. Am I audible now?
Yes, sir. Yes, sir.
Okay, I think I was in mute until now. I'm sorry for that.
No, sir.
I
Only
was
now
actually.
you were on mute.
Oh, all right, all right. So I was talking about the equations of motion of a robotic system, where we essentially find a relation between the forces or the generalized forces and torques to the trajectory of the robotic system, right? Because until now we have been just considering the geometric relations of a robotic manipulator, through the forward and inverse kinematics. We completely ignored what is the what causes the change of state of a robotic system, right? Like, for instance, I was I was actually explaining an example using a 2-hour robot earlier, right? If you have a 2-hour robot like this with some joint forces, supplied by the motors tau 1 and tau 2, and the task this robot is deployed on would impart some forces at the tip of the end effector, maybe due to the grasping of some objects. Maybe we can classify this external effects as the components of forces like Fx, Fi, and the moment component. And then due to the weight of, due to the mass of the links themselves, each of these links will be subjected to some, uh, you know, uh, of external disturbances due to the weight of the links themselves, and maybe due to, interactions with other bodies or interactions with the environment. They'll also be subjected to some external forces, maybe some contact forces like F2C or F1C. And then there could be, Fx due to friction. In each of these joints, there could be Fx due to friction and damping. So if you consider the direction of gravity to be vertically downwards, what will happen if you simply drop the robot from a rest position? What will happen? How will the trajectory of the end effector would look like? Or rather, how would the trajectory of the entire robot manipulator would look like? So to predict the change of state of a robotic manipulator, we would need uh, uh, a dynamic model of the robotic system that essentially maps the generalized forces and torques to the generalized position velocities and accelerations. So that is the purpose of why we need a dynamic model, right? To predict or to estimate the change of state of a robotic system as the time evolves. So if you reduce the dynamic system of all system of any robotic system can be, represented as a general form represented here. And we would be using this dynamic model for design, analysis, and control of robotic system. So in case of a design, a dynamic model can be used for designing the links, right? Depending upon how much forces are acting on these links, or maybe the reaction forces acting on either of the ends of a link, we can maybe either strengthen the links or maybe we can save some material. And then again, the forces that is acting on the link depends on how fast the link is moving, because if the link is moving very fast, the inertial effects will contribute to higher forces on the links. Or if the link is subjected to higher payloads, that will also need increased strength, strength of the links themselves. So for design purposes, we need the dynamic model. For analysis purposes also, we need dynamic model, right? For instance, if you want to predict the change of state of a robotic manipulator, we need a mathematical representation of a robotic manipulator, which would be provided by, the dynamic equations of motion. And then to control the system as well, right? For example, if you want to control the robot, along a desired trajectory, I would call this as a desired trajectory. And then, our robot start position would be somewhere around here, this could be the start position. So as the time evolves, we want the robot to gradually converge along the desired position, right? Initially, there will be some error, but as the time progresses, we want the robot to converge and follow the desired trajectory. So for choosing the control parameters, for choosing the optimal control parameters, we would need to know how the robot would behave to the control inputs. So for that purpose also, we need a dynamic representation of a mathematical representation of a robotic manipulator. So that's why we need to derive, the equations of motion for the purposes of design, analysis, and control of, robotic systems. And similar to, the forward and inverse kinematics, we also have a forward and inverse dynamics, dynamics problem, forward dynamics and inverse dynamics. So in case of a forward dynamics problem, for a given input vector torque or tau and the known states q dot, find the resultant motion of the manipulator, right? As I was saying, we can represent the equation of motion something like this, tau as m of q double dot plus n of q dot. This would be the general form of equation. And in case of a typical 2R robot, something like this would be the end effector. We have one input to the first joint, tau1. We have another input to the second joint, tau2. And maybe the robot is subjected to some, external forces, Fx, Fy, and maybe some moments, Mz, due to its application. So in forward dynamics problem, if we supply some control input to the joints, how would the robot react? How would the robot react to this control force? That is a problem that we are trying to solve, or we are trying to understand using the forward dynamics. So just like the forward kinematics, this is basically a simulation problem, right? We just want to simulate the robotic system and see how it reacts to some control inputs. Just observe how it reacts or how the state of the robot changes based on the control inputs. So if we have, a system of equations, something like this, and we also know, or we also provide the vector tau as an input to obtain the new change of state, we can rearrange this equation as tau minus n of q dot, the whole pre-multiplied by m of q inverse would give you q double dot, right? A simple rearranging of this equation would give you the accelerations. And if you integrate this equation, accelerations, with respect to time, you will get the subsequent velocities and the new updated positions as well, right? Provided your robot starts from an initial position and an initial velocity, how would the robot react? You can obtain the subsequent trajectory using this equation, which is a simple, rearrangement of, the standard equations of motion. And in the case of an inverse dynamics problem, it is defined as, for a given trajectory vectors q dot and q double dot, find the required input vector tau. Similar to the inverse kinematics problem. If we want the robotic manipulator to move along a desired trajectory, what should be the input, that we should be supplying to the motors, right? So that the robot can be controlled along the desired trajectory. So that problem is inverse dynamics. So I hope, without much confusion, we can basically see the parallels between forward and forward kinematics and dynamics, and the parallels between inverse kinematics as well as dynamics. Because the forward problem is always about analyzing the system, and inverse problem, be it dynamics or kinematics, it's about controlling the system, basically. Right. So I hope I'm still audible.
Yes, sir.
Okay, thank you. Now, now that we have established the importance of equations of motion, we would now see how to derive this equation of motion. So essentially, we have seen two principles, either one using the Euler-Lagrange method, which is what we will be discussing now. And later, we would be seeing how to derive this equation of motion using a recursive algorithm, a recursive algorithm called the Newton-Euler algorithm. But then we'll start with the Lagrangian algorithm. Basically, the scalar quantity Lagrangian can be defined as the difference between kinetic energy and potential energy. Like if you have a rigid body uh, uh, under observation, you can always associate the kinetic energy and potential energy of the rigid body with respect to its current positions and velocities. So the scalar quantity Lagrangian, it can be defined as the difference between kinetic energy and potential energy, right? It's nothing but the difference between Ke and Pe. And then you can essentially obtain the equation of motion by, expanding it according to this formula. So, you take the partial derivative of the Lagrangian with respect to the velocities first, then take the total derivative of this entire term with the time, subtracted by, the partial derivative of the Lagrangian with respect to the generalized coordinates. So this is essentially a vector equation. So depending on the kind of robotic manipulator that you are investigating, the vector Q, can have multiple joints. Maybe if you are considering about if you are basically dealing with a 2R robot, Q would be theta1 and theta2, which are the generalized coordinates that fully define the configuration of a robot. If you are dealing with an RR robot, the generalized coordinates would be theta1, theta2, theta3, for a robot with 3 revolute joints. If you are talking about an RP robot, which is a planar polar robot, the generalized coordinates would be theta1 and d2, which is a mixed vector of linear displacement and angular displacement. So like depending upon your robotic system, the vector of generalized coordinates would essentially change. That would fully define, the configuration of the robotic manipulator. And another scheme, which is a recursive scheme, is what we call as the Newton-Euler method, which essentially talks about the conservation of linear momentum and angular momentum. This expression is obtained by the conservation of linear momentum. If you take the derivative of the linear momentum, you will get the acceleration. So essentially, Newton's law says the external forces acting on a rigid body is equal to the mass of the rigid body multiplied by the acceleration of the center of mass, or acceleration of the center of gravity. Then Euler equation essentially says the net moment acting on the rigid body is nothing but the moment of inertia, the central moment of inertia multiplied by the angular acceleration of the robot plus this new term omega cross I omega, which is basically this basically denotes the change of linear momentum, right? In a when the linear momentum is expressed with respect to a rotatory frame of reference, you will get this term as well. The rate of change of angular momentum as well. But this term is only corresponding to the rate of change of angular velocities. Right. So we would see how we can use or how we can propagate the Newton's equation and Euler's equation so that the forces at relevant points of robotic manipulators can be determined. So for this recursive algorithm to work, we have to propagate velocities in the forward direction, right, from the ground all the way to the end effector. That is one propagation. And in the reverse direction, we will have to propagate the forces and moments. For example, if you have a robotic manipulator that is made of series of multiple rigid bodies, something like this, right? And maybe I'll consider the first join to be connected to the ground. maybe three links. The first joint is connected to the ground, second joint is connected to the first joint, and third joint is connected to the second joint. We would propagate, the velocities. What are the relevant velocities? Like we have the linear velocities, then we have the angular velocities, then we have the linear acceleration, then we have, angular acceleration. So starting from the ground, each, the total angular velocity of, or the total velocity and acceleration of this end effector would be influenced by all the preceding joints, right? Because if you consider a robot assembled of multiple actuated joints, each of the actuated joints would contribute to the linear velocities, angular velocities, linear acceleration, and angular velocity. So it will have a cumulative effect starting from ground all the way to the end effector, right? Obviously, for a robotic manipulator, the velocities and accelerations at the ground would be zero, right? And as we propagate in the forward direction, from the ground to the end effector, the velocities and accelerations get propagated or get accumulated due to the effects of, the actuated velocities, due to the effects of these actuators. So let's see how, we can propagate the velocities and accelerations. We have essentially seen the propagation of velocities in the previous class, when we were discussing about Jacobians, or, when we were discussing about the inverse differential kinematics and forward differential kinematics. So the first equation essentially says the propagation of angular velocities for a revolute joint. For example, if you have a revolute joint, if you have a link, maybe I call this as I, and we have another link over here, and I'll call this as I plus 1. And if I consider the joint to be vertically upward, Z I plus 1, the joint ZI plus 1 would be attached to link I, as per the DH convention. And for link I, we would be having the frame over here, ZI. So what this expression or this equation is nothing but a simple vector addition, right? We have already seen, how to add vectors with respect to two frames of references. Maybe, for example, if you have a fixed frame over here A, and if we have a moving frame B, something like this, and if we have a vector over here Q, which is expressed with respect to B, if we want to know the position, or if you want to know the position vector of Q with respect to A, from a basic vector addition principles, we can essentially say that position vector of Q with respect to A is position vector of B with respect to A plus position vector of Q with respect to B, right? This is nothing but a simple vector addition, where this is position vector of B with respect to A, and this one is position vector of Q with respect to B, and the total big length vector is nothing but position vector of Q with respect to A. But then when we are expressing vector additions, everything will have to be brought into, with respect to a single frame of reference. So this term and this term are already expressed with respect to the fixed frame of reference A, but the vector Q is represented with respect to the frame B, or the moving frame B. So to bring everything with respect to the fixed frame, we pre-multiply the vector with the correct rotation matrix, which is nothing but the rotation matrix of B with respect to A. Now, every vector quantity is represented with respect to a single, frame of reference. Right? In a similar manner, we can also, write this vector equation where, the angular velocity of the next link, or if you want to consider the angular velocity of this new link, omega I plus 1, that would be nothing but the angular velocity of the previous link, omega I, right? The angular velocity of the previous link plus the contribution by the rotary joint, right? If this is a rotary joint, the rotary joint can have its own rotation, right? It will have its own rotary degree of freedom. So we can express that using a vector, maybe I'll write it as 0, 0, theta I plus 1 dot, right? Because this vector will always be along the z-axis, because we all know that for a link I plus 1, a rigid body is attached to the link itself. A rigid body is attached to the link I plus 1 itself. So as the rigid body moves, or as the rigid body rotates, the frame I plus 1 will also rotate with respect to it, right? It will also always move with respect to it. So by ds convention, the z-axis is always pointing along the joint axis. So as a result, the angular velocity component caused by the motion of the joint itself can be represented like so, along the z component, because it's always aligned with respect to the z-axis. But then for the purposes of this recursion, we want everything to be expressed with respect to a single frame of reference. And for convenience, we want everything to be expressed with respect to the frame on which we are investigating, or frame at which we are currently investigating. So if you pre-multiply this general vector equation with a rotation matrix, I plus, maybe I plus 1 with respect to I plus 1, or with respect to I plus 1, and here also everything will be brought to the I plus 1 frame. If you do this, the left-hand side, would be omega I plus 1 expressed with respect to I plus 1. And the right-hand side would be omega I represented with respect to I plus 1. But this vector, since it's already expressed in I plus 1, the pre-multiplication of the rotation matrix will have no effect on it. So it will be again 0, 0, theta I plus 1 dot. So this is how we obtain this equation, right? The derivative of, the propagation of angular velocities from ith link to the I plus 1 link, right? This is how the angular velocities propagates. So when I is 0, for example, if you start from a rigid body, obviously the rigid body's angular velocities are going to be 0, because it's always fixed, right? The ground is always going to be fixed. So when I is 0, that concerns with the angular velocity of the ground, which is 0. This entire term will be 0. And the angular velocity of the first joint will be contributed by the rotary motion of the first joint itself. And as we propagate from the ground all the way to the end effector, we can recursively find out the angular velocities of the subsequent links. And in a similar manner, if you take the derivative of this expression, you will get the angular accelerations of, angular acceleration, the recursive equations for angular acceleration.
So this was forward or inverse dynamics?
I'm sorry.
This forward or inverse dynamics?
Inverse dynamics, no. we are not talking about inverse dynamics. Ultimately,
Forward dynamics.
for inverse or forward dynamics to work, uh, you would essentially need uh, you would need to find out the velocities. Because if you go back to this equation, yeah, if you find this expression, generalized expression, tau would be m of q multiplied by q double dot plus n of q dot. These vectors would consist of positions, velocities, and accelerations, right? So to find out the torque, uh, to find out the desired torque so that the robot follows a desired trajectory, we first need to find out, what is the trajectory or what is the positions, velocities, and accelerations on each of the joints. So that is why we need these propagation equations. Right? That's why we need to propagate the velocities first, because we have to estimate, the velocities, sorry, the positions, velocities, and accelerations uh, of each and every joint of the robotic manipulators. Then only we can substitute that into this equation so that the appropriate torque or the appropriate uh, force and the torques can be found out.
Yes,
So
sir.
the
So
first,
now you were
sorry,
simplifying. Now you were simplifying some equation. So that equation was what was it? I mean, uh, it was
these
velocity,
equations,
no? So yeah, so
these
that
equations.
was velocity or velocity, no? Sir.
Yeah, these are related to
Velocity
velocities.
acceleration.
These are related to velocities, right? For example, you will basically have a rigid body, serially connected rigid body, right? And the input that you would be giving are in terms of, the torques acting on each of the joints, something like
Yes,
this.
sir.
If this is tau 1, tau 2, tau 3, and tau 4. And then you'll also have an idea about how much each of these joints are rotating, right? Maybe if I represent the joint variable as theta1 for the first joint, depending on how you want the robot to move, you can also compute the velocities theta1 dot and theta1 double dot. Uh, the rotary displacement, the angular velocities and accelerations of this joint. And similarly, the joint 2 will also have its own displacements, theta 2 dot, and theta 2 double dot, right? We know the positions, velocities, and accelerations of each of these individual joints. But then for this for this recursive Newton-Euler algorithm to work, we need to find out what are the accelerations of the center of gravity of each of these links. What is the angular acceleration of, angular accelerations of the centroid of each of the links? What is the angular velocities of each of these links? So to find out these terms, omegas, accelerations of the center of gravity, angular accelerations of the individual links, we need these propagation equations,
Okay, sir. Okay.
right?
Got it.
We need these equations actually, so that it can be substituted into the Newton-Euler equations of motion. That's why we need these propagation equations. So I hope that is clear.
Yes, sir.
Okay. So the first equation deals with the propagation of angular velocities. The second equation deals with the propagation of angular accelerations. And the third equation deals with the propagation of linear acceleration. So that basically says the linear acceleration of the current link is nothing but the linear acceleration of the previous link, plus, we have this familiar looking term, which is, the tangential acceleration caused by the previous link. And then we also have the centripetal component, centripetal acceleration caused by the rotation of the previous joint, right? And everything, all of these terms will be shifted to the current frame, that is the I+1 frame, by pre-multiplying with the rotation matrix. So everything can be brought to the I+1 frame. And this is actually only valid for a revolute joint. If the current joint is a revolute joint, this is how the propagation equations would look like. But if we are dealing with the prismatic joints, maybe if the previous joint was a prismatic joint, and if the current joint is a prismatic joint, for example, I'll just depict here. If this is the I+1 link, and if this is the ith link, and I'll denote this to be the axis Zi+1 axis. So this link would be moving vertically up or down, along this Zi+1 axis, because it's a prismatic joint. So the angular velocity of the prismatic joint, angular velocity of the current I+1 joint would be nothing but the angular velocity of the previous joint itself, right? Because this joint does not have an angular component. It just moves back and forth. But effectively, as a resultant, if the previous link was rotating, this link will also rotate, right? Because they are rigidly connected, or they are connected with a joint. Even though this is sliding, because of the effect of the previous joint, it will also basically try to rotate. So what it says is angular velocity of the current joint, omega I+1, is nothing but the angular velocity of the previous joint for prismatic, joint. But since we are dealing with the recursive equations, we prefer to bring everything to the current frame, that is I+1. So if you multiply the rotation matrix I+1 with respect to I on both sides, I+1 with respect to I, we'll get the recursive relation. I+1 omega I+1 would be I+1 Ri multiplied by I omega I. So in case of a prismatic joint, the propagation of angular velocities would look something like this. And in a similar manner, the propagation of angular velocities would also look something like this. Right? It's nothing but the angular velocity of the current joint is angular velocity of the previous joint, but it is now brought to the current frame of reference. But then now the linear acceleration component is now a bit bigger than the previous case. The linear acceleration of the current joint is nothing but the linear acceleration of the previous joint. Maybe I'll write it here as the linear acceleration of the previous joint. And this term is the tangential acceleration. It's the tangential acceleration. We obtained this equation from this expression, from the recursive relations. This essentially denote the link length. If you have two joints, like something like this, if this is joint I, and if this is joint I+1, and if this is link I, and this is link I+1, the link length, the distance between frame I and I+1 can be expressed by a vector. The position vector of I+1 with respect to I, that is expressed in the ith frame. So if the cross product between the angular acceleration and this link length would give you the tangential acceleration, which is this component. And this component is nothing but the centripetal acceleration. And due to the relative sliding motion between I+1 and I, you will have two more terms. The first term is the slip, acceleration, slip, acceleration. Because the current joint is sliding, right? The current joint, Zi plus 1, is sliding with respect to its own axis, Zi plus 1, that is this component. And we'll have one more component called the Coriolis acceleration. Coriolis acceleration. That is nothing but the cross product between omega I plus 1 multiplied by the cross product between omega I plus 1 and d I plus 1 dot. That is nothing but the linear velocity of the current joint. Omega I plus 1 is the angular velocity of the current joint, which is obtained from these recursive relations. Right. So once you propagate the velocities in the forward direction, starting from ground all the way to the end effector, the next procedure is to propagate the forces and moments in the backward direction. Right. For example, if you consider a 2R robot, something like this, we have first joint, maybe I'll represent it as R1, and I'll represent it as R2. And if you have an end effector over here, so if you deploy a robot for a specific task, maybe for picking and placing an object or to grasp an object, whatever be the case, the end effector would be subjected to some a form of a wrench due to the interaction with the environment. So if you separate the final link or the final rigid body, right, something like this, and I'll call this to be the end effector. And due to its interaction with the environment, the end effector will be subjected to some forces, Fx, Fi, Mz. Maybe I'll call it collectively as the external forces, Fx external. And at this point, at probably this location, you will have the reaction forces. Maybe I'll label this as, Fi. And due to the, if there are reaction moments, we can also call it as the reaction moments, maybe small mi. And due to the fact that the link also has a mass, maybe I can probably characterize the mass of the link using the mass mi and maybe its moment of inertia, the tensor I. So if you consider, the force balance of the very final link, what are the forces that are acting on the link? Right? The net forces acting on this rigid body would be obtained by this force balance equation. This is nothing but the Newton's equation. Right? For example, if you want to know, the only unknown would be this one, Fi and Ni, which is the reaction forces and reaction moments acting on this joint. We know the external forces, the forces contributed by the external disturbances, and the only unknowns would be, this term, Fi and Ni. If you do a force balance equation with small Fi and Ni, the forces would be the net forces would be contributed by this reaction forces, the inertial forces, which is nothing but this equation, and also due to the external forces. Right. So this term, mass multiplied by the acceleration of the center of gravity, is nothing but the inertial forces, the linear inertial forces contributed by the motion of the rigid body itself. Right. And to obtain this acceleration of the center of gravity, we need one more equation actually. This is also a propagation equation, not necessarily a propagation. For example, if you have a rigid body, something like this, And if this is the location of the center of gravity, somewhere close to the center, I label this as rigid body I. And as per the DS convention, you will have a frame of reference attached to the proximal end. I'll label this as Zi, and this axis to be Xi. So if you know the acceleration of this point, acceleration of this point I, because this point is I and this point is I plus 1. And this point I'll call this as Ci. This is nothing but the location of the center of gravity. So if you know the acceleration of this point, the proximal point, from the forward propagation, from the forward propagation equations that we have seen earlier, what will be the acceleration of this point Ci? That is nothing but the acceleration of, this point, or acceleration of this point, that is given by this vector quantity. Then we have a tangential component, which is nothing but alpha I, the angular acceleration of this point, multiplied cross producted with this distance, from I to Ci. That is denoted by this vector IPCI. Alpha cross IPCI would give you the tangential component, and then the radial component, omega cross IPCI. If you have the angular velocity omega I known from the forward propagation of this point, then the centripetal component would be omega I cross this distance, position vector of Ci with respect to I, denoted by this vector quantity. And once you obtain this expression, or once you obtain the value for the acceleration of the center of mass, you substitute that into this equation to obtain the inertial acceleration, or the inertial forces. And a similar thing will also go into the moments as well, right? So the moments, the inertial moment can be obtained by the Euler equation, which is nothing but the moment of inertia multiplied by the angular acceleration of the ith point, then omega I cross I multiplied by I omega I. So this is the Euler equation, and this is the Newton equation. And in case of a Newton equation, you can obtain this term, the acceleration of the center of mass, by this equation. And the Euler equation, you can directly obtain everything from the all these quantities will be available from the forward propagation of velocities and accelerations. And once you obtain all these terms, you do a backward propagation of forces, which is given by this equation, and backward propagation of moments, something like this. So if you consider a rigid body, maybe an ith rigid body, if this is ith rigid body, you have the reaction forces and moments at the ith point as Fi and Ni. The reaction forces at the I plus 1 point to be, Fi plus 1 and Ni plus 1. And then you also have the component of the inertial forces, that is Fi, and the inertial moments Ni. So if you do a simple force balance, the net forces, or the force acting on this end, Fi, is nothing but Fi plus 1 plus the inertial component. But now, since we are representing everything with respect to the ith frame, for the purposes of this recursion, the forces Fi plus 1 would be brought back to the ith frame using this rotation matrix, and it will be added with the inertial component. This is a simple force balance, right? And at the very distal end, at the very final link, this term would be the external forces. This term would be the external forces. And in the subsequent iterations, you will be able to obtain the forces starting from the external force all the way to the ground link using the backward propagation. And the same thing can also be applied for the moment balance equations as well, because the moment at this point, Ni would be the moment contributed moment at this point, Ni plus 1, plus the moment contributed by this force Fi plus 1. That is nothing but this distance cross producted with this force. We have that term over here. We have that term over here. Then we have the moment contributed by the inertia, which is this term, and the moment contributed by the the inertial force Fi, that is this term. And then finally, that's about it actually. We have the moment contributed by Ni plus 1, moment contributed by Fi plus 1. That is nothing but this distance multiplied by this force. When we have the moment contributed by the inertia, which is Ni, then the moment contributed by the inertial force is Fi, which is nothing but this distance cross-producted with this Fi. So that will give you the moment balance equation. So if you carry this throughout in the recursive backward direction, you will obtain all the components of moment acting on each and every joint. So these are all vector equations, right? So for each and every joint, you will obtain the 3 components of forces and you will obtain the 3 components of moments. But in case of Lagrange equations of motion, since you are deriving everything in the generalized coordinates, you will only get the forces and moments along the corresponding joints, right, in the direction of the joints. But in case of a Newton-Euler method, you will get all the components, not only the components along the joints, but along the other axes as well. So this can be beneficial if you're trying to design a robotic manipulator, because on top of the actuation forces, you would also get information regarding the reaction forces, the components of reaction forces and reaction moments. That will be very suitable for modeling or designing individual links. Yeah. So again, this is a systematic procedure. First, you have to propagate the forces. First you have to propagate the velocities in the forward direction, and then you propagate the forces and moments in the reverse direction, and then substitute everything into the Newton-Euler equation, which is this one for the inertial forces and for this one for the inertial moments, and then do the force balances and moment balances for each individual, each and every individual helix. So that's how you will obtain the forces and moments acting on each and every joint for any corresponding trajectory. Right. So now we'll do some sample tutorial questions because this is what we would like to discuss regarding dynamics. Right. So the first question is a true or false question. So in case of a serial fixed base manipulators, the force and moment vectors of individual joints are obtained by forward propagation. Would that be true or false? If you have a series of rigid bodies, something like this. I think just now only we have seen, 2 directions of propagation. So, if we consider this side to be the ground side, closer to the ground, and this side to be the end effector side. We start with the zero velocities, accelerations, be it linear or angular components at the ground. And then we propagate due to the effect of the individual joints, each of these joints will influence the velocities and accelerations of the end effector. So the cumulative effect, imparted by each of these individual joints can be understood or can be derived using the forward propagation of velocities and accelerations. Starting from the ground frame all the way to the end effector frame. And once you have obtained the velocities and accelerations, the next step would be to compute the inertial forces and moments, right? Using the Newton's equations and Euler equations of motion. Once you obtain the inertial forces and moments, then you do the backward propagation, right? In this direction, you do the backward propagation of forces and moments. Right? So ultimately, your aim is to find a function or find a mapping between the trajectory characterized by positions, velocities, and acceleration to the forces, acting on the joints. So in case of a recursive Newton-Euler method or procedure, what you do is first you propagate the velocities, then you find out the inertial forces and moments. Once you do that, you do the backward propagation by taking the force balance and moment balance for each and every link of the robot. So in that regard, you will get a mapping between velocities, accelerations, and the forces and moments acting on the joints. So in that regard, the statement that's saying in serial manipulators, the forces and moment vectors of individual joints are obtained by forward propagation. That is actually false, right? Because forces and moments are obtained by backward propagation instead of a forward propagation. So that answer is obviously a false statement. Yeah, that is indeed true. Now, moving on to the second question. If M of mu is the inertia matrix in task space and J of Q is the Jacobian matrix, what will be the vector of Coriolis and centrifugal effects in task space? So this is a good question. So let us begin with what we currently know of, or what we are familiar with. So we can write the equation of motion in the joint space coordinates as something like something as follows. Maybe equation of motion in joint space. We can write it as tau would be a mass matrix of Q multiplied by Q double dot plus N of Q dot. I'll label this as the dynamics equations of motions. So in case of a 2R robot, something like this, the generalized coordinates would be, the joint variables theta1 and theta2, which would fully define the configuration of the robot. So Q would be theta1 and theta2. Q dot would be theta 1 dot and theta 2 dot. And Q double dot would be theta 1 double dot and theta 2 double dot. Since we are using theta 1 and theta 2 as the generalized coordinates, the vector of forces and moments tau would be tau 1 and tau 2, where tau 1 would be the torque acting on this joint, along the direction of the revolute joint. And tau 2 would also be the torque acting at the second joint along the direction of the second revolute joint. But then the question asks you to find, an equation of motion in task space. So instead of writing this equation of motion in task space, we can write the same equation of motion in a Cartesian space or in task space instead of joint space. So that would look something like F would be a mass matrix M of mu multiplied by eta double dot plus N of mu. This would how the equations of motion would look like in task space, where eta dot would be the vector of eta would be a vector of Cartesian positions x and y. Eta dot would be x dot and y dot, and eta double dot would be x double dot and y double dot. So you can represent it, whichever coordinates or whichever coordinates you wish. You can represent the equation of motion in task space or in joint space. But then we would start from this joint space equation and see how we can relate, or what is the relationship between this q double dot and eta double dot. What is the relationship between this m and m of q and m of mu, and what is the relationship between n of q dot and n of eta in task space. So we know that in joint space, this is how the equations of motion would look like. And from kinematics, we know the mapping between joint space and task space using this expression. Eta dot would be the Jacobian J of q multiplied by q dot. This would be the kinematic mapping, between task space and joint space. So I'll just erase all this. So if I take the derivative of this expression, or I'll differentiate this expression with respect to time, you will get eta double dot would be J of q multiplied by q double dot plus J of q dot multiplied by q dot. So if I substitute this expression, substitute, or before that, I'll just rearrange this equation, right? If I rearrange this expression, now eta double dot minus J dot of q dot, the whole pre-multiplied by J of q inverse, I'm just rearranging this equation to obtain q double dot. Right? So now your q double dot would look something like this. And if I substitute this onto the dynamics equation, I'll substitute into dynamics, which is, this equation. I will end up with tau would be m of q. Instead of q double dot, I'll use this expression, that is J of q inverse eta double dot minus J dot of q dot plus now this term plus N of Q, Q dot. Now, if I expand this, expand this bracket, what I would be getting is tau would be M of Q, J of Q inverse, eta double dot, minus M of Q, J of Q inverse, J of Q dot, Q double dot, Q dot plus N of Q, Q dot. This would be your tau. Now, again, in the previous class, we have also derived, from the conservation of power, we have also seen the mapping between the vector of generalized forces and moments tau and the forces in the task space, which is nothing but tau would be J transpose F. We can obtain this relation from the conservation of power. So if I substitute this expression, J transpose F over here in place of tau, you will get J transpose F would be M of Q, J of Q inverse, eta double dot minus M of Q, J of Q inverse, J dot of Q, Q dot plus N of Q, Q dot. Now, if I bring this J transpose to this side, to the other side of the equality, you will get F as J inverse transpose of Q, M of Q, J of Q inverse, eta double dot minus J inverse transpose of Q, M of Q, J of Q inverse, J dot of Q, Q dot plus J inverse transpose of Q, N of Q, Q dot. And if you compare the general form of the task space equation here and to what we have derived here, the mass matrix is the coefficient of eta double dot. So here eta double dot is this term, and the coefficient of mass matrix, coefficient of eta double dot would be this term. So I'll write this term as mass matrix M of mu, and whatever left would be the vector of Coriolis and centrifugal effects. So this entire term over here would be the vector of Coriolis and centrifugal effects. So here, if you take a look at this, there is also one more J inverse transpose M J inverse, right? A term like this. We also have the same term over here. So I'll write that part as M of mu. Then I'll carry over these two terms. J dot of Q, Q dot, there is also minus here, plus J inverse transpose Q, N of Q, Q dot. So this term would be the vector of, N of mu. This term now would be the vector of centrifugal and Coriolis effects expressed in task space coordinates. So from this equation, from the MCQs, I believe the correct answer would be, this term would be over here, and this term would be over here. I think it should be option D. Yeah, I think that is correct answer. That is how you derive, We have considered, the dynamics. We have considered the kinematic mapping between task space and joint space. And we have also considered the mapping between joints in the generalized force coordinates and the forces in the task space. We derived this expression from conservation of power. We have discussed that in the previous class. So yeah, option D is indeed the correct option. And now we'll move on to question 3. It says it's a true or false question. Inverse dynamics problem is simulating or analyzing the manipulator. Is it true or false? So like we have seen the forward dynamics, and we have seen the inverse dynamics. And if you consider a generic robotic system of the form, maybe tau would be a mass metric sum of q double dot plus n of q. In case of a forward dynamics, we supply the torque and then we obtain this q dot and see how the system reacts. Right? The input torques are provided by the user itself, and see how the system reacts to the input torque primarily and the external effects. So the forward dynamics, in essence, is like a simulation, right? We give some supply or we give some input and see how the system reacts on a virtual level. It's very similar to the forward kinematics. We give some inputs directly to the motors and see how the system reacts or how the geometry of the robot changes. A similar analogy can be brought to the forward dynamics as well, because all the forward problem is an act of simulating or analyzing the mechanism, whereas the inverse problems, be it kinematics or dynamics, is similar to controlling the robot to follow along a desired trajectory. So the statement over here, inverse dynamics is the problem of simulating or analyzing. That's obviously false, because simulating or analyzing always applies to either forward dynamics or forward kinematics. So in that regard, we can classify the option to be false, right? Because it's contradictory with each other. Yeah, that's indeed false. Moving on to question 4, the angular acceleration propagation model of a rotary joint is given as. Again, you are essentially asked to reproduce a formula regarding the forward propagation of angular acceleration. Right? So the easiest way to represent it, easiest way to understand this is that the angular acceleration of the next joint would be the angular acceleration of the current joint, alpha I plus the contribution by the angular acceleration of the joint itself. Like if it's a rotary joint, the rotary joint can have a linear velocity and an angular velocity. So we'll have the term 0, 0 theta I plus 1 dot plus, due to the coupling effect of the angular velocity of the previous joint, we'll also have one more coupling term, something like this, I omega I plus 1 cross producted with 0, 0 theta I plus 1 dot. And then we have to bring everything back to the I plus 1 frame. All these things will have to be brought to the I plus 1 frame. This part over here, this was already represented with respect to I plus 1 frame. Because, every rigid body has its own coordinate system that is attached to the rigid body itself. So if an I plus 1 rigid body is a rotary joint, the angular velocities and angular accelerations are represented with respect to its own local z-axis. So that's why we are getting this term over here, theta I plus 1 double dot. And if you bring everything, because since this is a recursive equation, everything is everything of the previous link was expressed with respect to the previous link itself, but now it has to be brought back to the current link because it's a recursive equation. So you pre-multiply this equation with a rotation matrix, that is the rotation of I with respect to I plus 1. So in that regard, I believe the correct answer is to be option A, I suppose. Option A itself. Because in all the other terms, yeah, this is not correct. This won't make it recursive, right? Because for it to be recursive, these terms, alpha of the previous link should be expressed with respect to I itself, and alpha of the current link with respect to, it should be expressed with respect to I plus 1. So this term won't qualify. Again, this term won't qualify. This term, they have used a wrong rotation matrix. Instead of this, we want it to be expressed like this, right? And this term, this option has a similar issue. This option also has a similar issue. Right? Everything has to be brought back to the I plus 1 frame, not the other way around. So option A is indeed the correct answer. Moving on to question 5. Deriving equations of motion using Newton-Euler method is a two-stage process. Stage 1 being the forward propagation of velocities, and stage 2 being the backward propagation of forces and moments. So that is already true. We have discussed this many times. The first part is about propagating the velocities and accelerations from ground all the way to the distal end effector. And once you have obtained the forces, once you have obtained the velocities and accelerations, you would then find out the inertial forces and moments. And once you obtain the inertial forces and moments, you do the force balance, in the reverse direction, or you do the force balance or the force propagation in the backward direction. So you will be able to obtain the forces and torques acting on each joints. So the statement is indeed true. It concerns about forward propagation of velocities and backward propagation of forces and moments. So that's obviously a true statement. So we label it as a true statement. And now moving on to question 6. It's a numerical problem. The angular velocity of ith link expressed in its own coordinate frame is given as 0, 1, 2. So I omega I is given as 0, 1, 2. So the following link I plus 1 rotates with an angular velocity of 4 radians per second. So link I plus 1, maybe I'll write it as, the link rotates theta I plus 1 with respect to I plus 1 dot, this would be 0, 0, 4, right? It rotates with an angular velocity of 4 radians per second about the z axis of its own coordinate frame. So that's why I've written it as 0, 0, 0, 4. Given the matrix of, given the rotation matrix, I plus 1 with respect to I, this is given as 0, 0, 1, 1, 0, 0, 0, 1, 0. What is the angular velocity of the next link, omega I plus 1, expressed with respect to I plus 1? This is what the question asks. So the context of this problem is as follows. We have a link I, and we have a link I plus 1. And here we attach a frame to the I plus 1 link. This would be Z I plus 1. This would be Xi plus 1. And the link I plus 1 would be rotating about Z I plus 1 by an angular velocity theta I plus 1 dot, which is given as 4 radians per second. And for the ith link, you will have a frame attached here over here, Zi, Xi would be something like this. And the angular velocity of this frame, angular velocity of this frame, I omega I is given as 0, 1, 2. This could be due to the if there are previous links, maybe I minus 1, the effect of the previous links accumulated at the link I would give you a vector of 0, 1. That's what it basically means. So what is the angular velocity omega I plus 1 with respect to I plus 1? How do we do that? So, basically a vector equation would look something like this. Omega I plus 1 would be omega I plus theta I plus 1. So we already know theta I plus 1 is represented represented with respect to the I plus 1 frame. This would be represented with respect to I plus 1. Omega I in the question, it was already given with respect to I. And we want omega I plus 1 to be referred in its own frame of reference, I plus 1. So this is what we desire. We already have this information. We have this information, but here you can see it is referred with respect to the ith frame. So to bring this to the I plus 1 frame, we pre-multiply that with the rotation matrix, I plus 1 with respect to I. That is what we got. We were provided in the question itself. So now, taking everything together, we'll have 0, 0, 1, 1, 0, 0, then 0, 1, 0. This multiplied by omega I would be 0, 1, 2, plus the relative component, that will be 0, 0, 4. If you expand this out, you will obtain 2, 0, 1 plus 0, 0, 4, which will give you 2, 0, 5. This would be the angular velocity component of link I plus 1 with respect to I plus 1. So the correct answer is 205. I think the option is option D, 205. All right, so let's check the answer. It's indeed 205. And now, moving on to question 7. This is also a numerical problem. Looks similar to the previous problem. Angular velocity of ith link expressed in its own frame is given as 201. So I omega I, this is given as 201. Right? And angular acceleration vector is given as I alpha I, this is given as 220. The following link I plus 1 rotates with an angular velocity and angular acceleration of 2 radians per second and 3 radians per second square. So theta I plus 1 dot would be 0, 0, 2, and theta I plus 1 double dot would be 0, 0, 3. Both about their z-axis of its own coordinate frame. So since it's rotating with respect to its own coordinate frame, and due to the fact that the joint is aligned with respect to the z-axis itself, we only have a single component that is on the z-axis. Given the rotation matrix I r I plus 1, this is given as minus 1, 0, 0, 0, 0, 1, 0, minus 1, 0. determine the acceleration vector alpha I plus 1 represented with respect to I plus 1. This is what the question is asking. Right? So again, we have to do the the recursive relations in that case. So how do we proceed? How do we obtain the recursive relations? So what exactly was the recursive relation? I believe the recursive relation was I plus 1 alpha I plus 1. This is obtained as I alpha I plus I omega I cross producted with I plus 1 theta I plus 1, and we pre-multiply or we bring all of these into the I plus 1 frame using this matrix I plus 1 Ri. Then we add with the final relative acceleration 0, 0 theta I plus 1 double dot. So you are given the inverted rotation matrix, but we want this I plus 1 Ri. Instead, we were given I Ri plus 1. So since the rotation matrix is orthonormal, to find its inverse, we can just take its transpose as well. So this will become minus 1, 0, 0, then 0, 0, 1, then 0, minus 1, 0. This quantity multiplied by I alpha I is given as 2, 2, 0. Then we have a cross product to be evaluated. So I'll represent it as a determinant. I j k, I omega I is 2, 0, 1. And I plus 1 theta I plus 1 is 0, 0, 2. Then this term added with 0, 0, 3. So if I expand this out, I'll get as minus 1, 0, 0, 0, 0, 1, 0, minus 1, 0. This multiplied by 2, 2, 0, plus, if I take the determinant, what will I get? I'll get it as minus 4j, I believe. So this will be like 0, minus 4, 0, plus 0, 0, 3. So if I take the vector sum inside, I'll get it as 2 minus 2, 0, I believe, inside this big bracket. Should be like 2 minus 2, 0. And if I multiply this matrices out, I'll get it as minus 2, 0, and minus 2, I believe, plus 0, 0, 3, and I'll get it as minus 2, 0, 1. This would be our angular acceleration of I plus 1 with respect to I plus 1. So the correct answer is indeed, option B. So one thing I would like to note is that, these sort of expressions, for the purposes of this course, it's better to, by heart it or learn it on your own. These sort of expressions. But generally, these are derived from rigid body dynamics or rigid body dynamics. So if you refer to any rigid body textbooks or any rigid body textbooks, you will be able to obtain this expression and how these were derived. Right? Like we have discussed a simple version of this equation in the second or third week. To take a derivative of a vector that is attached to a rotating frame of reference. So a similar principle will also apply here, right? If you consider angular velocities, if you take the angular derivative of angular velocities, you will obtain the angular accelerations. but then you should be able to know how to take the derivative of vector in a rotating frame of reference. All right, that's question 7. The option is indeed option B. Moving on to question 2, again, this is asking the propagation, forward propagation of linear acceleration, right? So we essentially know that the linear acceleration of I plus 1 would be the linear acceleration of the ith component, plus we have a centripetal component, we have a tangential component, alpha I cross I plus 1. Then we have the centripetal component, I omega I cross I omega I cross I plus 1. These are the components we have for if the joint is a rotary joint. And since this is recursive, all the quantities of ith frame, they are referred with respect to ith frame only, right? And this term is also referred with respect to the ith frame. But we want everything referred with respect to the I plus 1 frame, for it to be recursive. So we pre-multiply all of these equations with the rotation matrix that maps the quantities from ith frame to the I plus 1 frame. So in this regard, I think option A looks the correct option, I think. Option A itself is the correct option. Because in this case, the rotation matrix is not correct, it's flipped. Here, rotation matrix of ith frame with respect to, its own frame, it's an identity matrix, right? There is no rotation matrix. And in this case, this is not a recursive relation, right? Because A is referred with respect to, again, this is wrong. It's absolutely wrong. And in this case also, the rotation matrix is not correct. In this case also, the rotation matrix is not correct, actually. It's not a recursive relation. So the correct answer in this case is option A. Moving on to question 9. This basically talks about the backward recursion of moments. So as I was saying earlier, if you have a rigid body, this point, if you have a rigid body I, over here you have the ith frame. Maybe I'll label this as Zi. This would be frame I. And over here you have Zi plus 1 frame. I'll label this as I plus 1. But it should be noted that only ith frame is attached to the rigid body I, whereas I plus 1 frame would be attached to the rigid body I plus 1. So what are the forces that are acting on the rigid body I? You will have the reaction forces at this end, Fi plus 1. You will have the reaction moments at this end, Ni plus 1. You will have the reaction forces at end I, which is Fi, reaction moments, Ni. And then here you will have the inertial forces, Fi, at the center of mass. And you will also have the inertial moments, that is Ni. So if you take the force balance, the question asks you to find the joint torque or the moment balance. So if you take the moment balance, Ni or Ini, since we are doing the backward recursion, we would be knowing the forces at I plus 1 end, and we want to find out the forces and moments at the ith end. So the moment here would be the sum of the inertial moment, that is Ni, this portion, and then we'll have the moment contributed by Ni plus 1, plus we'll have this Ni plus 1, This is obviously represented with respect to the I+1 frame. But since we want everything to be represented with respect to I frame, we have to pre-multiply this with the correct rotation matrix. That will be I+1 with respect to I. Then what other moments we have? We have the moment contributed by this force, right? Because this force is at a distance, at this distance. So this force will have a moment at this point because of this moment arm. So I'll denote this moment arm or that distance as the position vector of I+1 with respect to I, which would be this distance. So the moment contributed by Fi+1 would be Fi+1, that is referred with respect to I+1, but we have to bring it back to the ith frame. So I pre-multiply that with the rotation matrix I+1 with respect to I. Then I have to cross product that with I+1. Then we have covered this one. We have covered this one. We have covered Ni. We also need to cover this moment contributed by this force, inertial force Fi, due to the moment R, contributed by this distance. So this distance, the distance between I and the center of mass, I label this as position vector of Ci with respect to I. So the moment contributed by Fi would be I Pci cross Fi. Right? So now how many terms we have? We have Ni, we have this term over here, we have this term over here, we have this term. So we have 4 terms. 4 terms contributed to the moment at ith chart. So the correct option in that regard is, I think this looks correct to me. Yeah, this equation B looks correct, actually. Yeah, inconsistent with the notations that we have. So option B is the correct answer. Question 10. For a given single rotary link manipulator, what will be the potential energy? So this is a single pendulum. Maybe you can call this to be an inverted pendulum with a link and a mass attached at the very tip. So the entire mass of this body is concentrated at this tip at a length L. So how do you define the potential energy? If you consider this x-axis to be the datum, the mass is actually at a height, if you at a height of h units. So this potential energy is nothing but mg multiplied by h. So from this basic relation, h is nothing but L. If this angle is theta, h would be L cos theta. Right? So potential energy would be mgl cos theta. Expressed in terms of that generalized coordinate theta. So I believe the answer is mgl cos theta. Yes. And for question 11, for a single rotary link manipulator in the figure, what will be the kinetic energy? So kinetic energy of a mass or a point mass is nothing but half mass multiplied by its velocity, half mv square. But then how do you find the velocity? Velocity is nothing but, if you decompose the velocity v square as vx square plus vy square, what is this Vx? Vx is nothing but derivative of the x position with respect to time, and Vy is nothing but the derivative of y position with respect to time. So we know the x position of the point mass is minus L sine theta, and y position would be L cos theta, and dx by dt would be minus L cos theta multiplied by theta dot, chain rule, and dy by dt would be minus L sine theta, theta dot. So this is nothing but Vx and this is nothing but Vy. So Vx square plus Vy square would be L square cos square theta, theta dot square plus L square sine square theta, sine square theta, theta dot square. This is nothing but L square theta dot square. This is basically Vx square plus Vy square. This is nothing but resultant velocity square. So kinetic energy would be half mv square, that is half m L square theta dot square. So here instead of theta dot, the question has given you omega. So the correct answer in this context would be half m L square omega square. The answer is option C. So since once you have obtained kinetic energy and potential energy, you can obtain the Lagrangian using, Lagrangian is defined as the difference between Ke and Te. And once you have obtained that, you can take the derivative of the Lagrangian with respect to theta dot, and the resulting expression, you can take the total derivative with respect to time. And if you subtract from this term, dou L by dou theta, you will get the torque acting on this joint. So if you do this, you will get the torque acting on, the torque tau acting on this revolution joint. Because you have already obtained the expressions for Ke and Te, substitute that into this Lagrangian equation. And once you obtain, you do the partial derivatives, you will be able to find out the torque, acting on that joint. So similarly, if you have multiple rigid bodies, you can, instead of this theta dot, you will have a vector equation. Theta dot would be theta 1 dot, theta 2 dot, you will have a vector equation. And correspondingly, you will obtain, the appropriate torques or forces acting on either of those joints. So in that regard, the correct answer is option C. Yeah. So with that, I would like to conclude our discussions on dynamics. Essentially, it's it may seem rigorous, but it's a matter of just following the procedure. The forward propagation of velocities and the reverse propagation of forces and moments. And once you obtain the velocities and forces, once you do the forward propagation and once you do the reverse propagation, you will be able to obtain the required torques and forces for a given desired trajectory. Okay, so that's about it. If there are any questions, let me know. Otherwise, if there are any doubts or questions, let me know. Otherwise, we can wind up this session. Any doubts regarding today's lecture?
What is the textbook we can follow for this?
I mean, if you are interested to obtain or to understand the derivations, there is a textbook called Introduction to Robotics by John J. Craig. John J. Craig, C-R-A-I-G. I believe the name of the textbook is Introduction to Robotics.
Okay, okay, sir. JJ Kreiswa. Okay.
Yeah, JJ Craig. Yes. I believe that would be a good textbook to follow for the mechanics part for the dynamics actually, because they begin from the fundamentals actually. First they do the vector addition, then they take the derivative of vectors, and in place of the vectors they would substitute the angular velocities, and then they take the derivative of angular velocities to get the expressions for angular accelerations. Similarly for linear velocities and accelerations. It's a very good textbook, I think, to follow. Okay. Yeah, that's from my end. Okay, so yeah, for the from the context of this course, you are really required to follow the recursive expressions. If you want to solve the weekly quizzes, the question pattern is more or less similar to what we discuss over here. Pretty much similar. Okay, so that's about it. I shall wind up this session. Thanks for joining. Yeah, thank you.
Thank you.